Hey everybody, it is Skill Cat Friday, which is weird, right? Usually it's Skill Cat Tuesday. But we're here because we have a very special episode of our HVA Chicks live training series. And today I was going to teach this class by myself. And then I got to thinking that it's refrigeration theory. So my best friend happens to be like the lord of refrigeration. So it didn't make much sense for me to do this alone. So I asked Mr. Brett Wetzel of Advanced Refrigeration Podcast to join me. So, you guys, this is again our merge series. It is our HVHX live training series that is brought to you all by Intersportsnet's Elite Trade Championship, HVACnationals.com. And it's also our SkillCat weekly webinar training. So, thank you for being here with me, Brett.
No problem.
So, first, I want to talk about getting into how did we get here, right? Like, there have been so many advancements in refrigeration over the course of the last 100 years. And even before that, there were many, many, many ways that we were conditioning our homes and our businesses. None of them really came through, obviously, until the great Mr. Willis Carrier, got it on lock. But there were other ways. So I want to talk about how we started. We'll do like that TikTok challenge, where we started and where we're at kind of deal. So where we started in refrigeration, guys, I'm going to share my screen. Oh, it's disabled. B, do you have a way to give me access?
Oh, way to break it. Gotta apparently make you do I gotta make you the host again or what?
I don't know.
We're just gonna trade off and
Sure,
on.
we'll just trade. And when you're ready to present, I'll send it back.
Unbelievable.
And this
See,
is
I've never
why Brett
oh,
wishes he said no.
this is all awful. Hold on. Now I gotta figure out how to give you hosting now.
All right, down at the bottom,
Mm-hmm.
or in more, it should say host. Oh no, actually, click on participants and then click my name and click the three little dots, or hover over my name, click the three little dots. Oh, I can reclaim it right here. I'm the host now.
Unbelievable.
Okay.
Unbelievable.
Sorry, guys. We're just going to trade host responsibilities back and forth here. So I just wanted to kind of touch on this a little bit. I'm not sharing my slide deck for this today because Brett's is so much better than mine because that's what he does because he's awesome. But I wanted to touch on a couple of things. So in the beginning, we, obviously had air movement as a way of conditioning our homes. And it didn't work super well because as we know, we're just moving the air around. We're not actually conditioning anything. But there were problems with that. And one of those problems that we don't think about a lot is not just comfort, but it's also health. So there were many, many different health issues that were exacerbated by heat. So in 1842, John Gorey, the wonderful John Gorey, is one of my favorite scientists ever, came up with an idea. And he said, we have a serious, serious problem with yellow fever right now. And in the hospitals, they're not able to keep the rooms cool enough. And these people are dying when there was no need of it. They, if we could have kept them cool long enough for their fever to break, they would have been all right. So John Gorey wanted to come up with something. So he tried many, many different things. There were actually scientists before him who brought giant chunks of ice, from the lake up into the front of the hospital and just blew the air in the window. Like there have been so many different ways that we've tried to do this, but John Gorey was the first to really find a way that didn't cause severe back pain for the people involved. So I'm just going to read this to you. John Gorey, an American physician, is credited with inventing the ice machine for cooling air. In 1842, he designed and built an air cooling apparatus to treat yellow fever patients. His basic principle involved compressing a gas, cooling it through radiating coils, and then expanding it to lower the temperature further, a concept still used in modern refrigerators today. Gorey's pioneering work laid the foundation for air conditioning and refrigeration systems that we rely on today. So this is interesting, you guys, because it seems like such a simple concept, but it's exactly what we're doing now. And then on top of that, we use this for much larger applications as well. Actually, I was lucky enough to get hooked up with one of the NASA engineers, and he explained to me that this is exactly how it is done on rocket ships. It's just a radiator with cooling fluid in it and, goes back to the back of the rocket, goes back to the front of the rocket. No different than what John Gorey was doing all that time ago. The difference was Gorey didn't have the right gas. And now we know that, possibly he did have the right gas. He just wasn't using it correctly.
Wait a minute. What gas was he using?
So he tried many, many different gases. The one that he eventually settled on was ammonia, which is the right gas, right? just not in this application. With ammonia, we've got to use an absorption system to make it work to its full potential. But that's not what this was.
No, we
So,
don't.
well, you have stuff in supermarkets situations, but I'm talking about to cool homes.
Yeah, you can still use a mechanical cooling. Same principle, same concept.
All right, walk us through it.
Well, I mean, it's all about saturated, right? I mean, what do we do?
Wait, is
We're,
it still sharing? Can you see my other screen?
I can't see anything. You're frozen. No, you're not frozen.
What? Okay, hold on. Oh, because I didn't hit share. Stupid. Oh my God, what just happened? Okay. All right. Now can you see it?
Now I can.
Okay. So yeah, we'll talk about that after because Brett is actually technically right. Like, yes, we could cool homes with ammonia. It's just not ideal
Oh,
compared to
it's the safety aspect to it. That's the only thing.
that too. Yeah. So it's a severely toxic refrigerant for those of you who don't know. Wait. I think we have somebody in the waiting room. Just want to make sure it shrunk my little doodad. Nope, he's not here yet. All right. So this is the other thing that I wanted to show you, or another thing I wanted to show you guys. Except it's going to scroll super slow all of a sudden. All right. So the next thing that we did was to move that into businesses and to make it more widespread, right? So we had it in hospitals at that point. It wasn't perfect, but it was working. So many engineers decided that that was going to be their undertaking. And many tried and failed to do what the great Willis Carrier ended up doing. So he was 25 years old. And this is what people think of Willis Carrier, and they think of this old man picture of Willis, standing next to his air conditioner. That is the end result of Willis Carrier. The beginning, Willis Carrier was a firecracker. He was 25 years old, and he was very much experimental. He was not somebody that the wider engineering world would have just trusted and said, oh, well, if he says it, it's true. He was definitely not one that they were going to put up on a pedestal and say he can make decisions for us. They did not trust Willis Carrier. And looking back, in hindsight, that's pretty crazy to us. But the first one that he was able to come up with was a more primitive cooling system, but it reduced the humidity around the printer. So he was checking out a printing company and realized that the pages were sticking together. There was a lot of humidity in the room where they were storing all these papers, and they had to come up with a way to fix this because it was costing the printing company thousands of dollars. So he used an industrial fan to blow air over steam coils that were filled with cold water. The excess humidity would then condense on the coils and produce cooled air. Sounds simple, right? Not only did it solve the problem, but the cool air started to make people comfortable. And then the light bulb went off. So this is a picture of it. And I just wanted to show you guys kind of how far we've come. So it's funny because this is, for lack of a better word, a hydronic system. And when you look at it, it looks like an industrial boiler. It doesn't look like an air conditioner, right? But that's exactly what it is. So there's actually one of these left. There's 4 left in the United States, I believe, but this one is in the Smithsonian collection, which I would really love to go and look at someday. I don't know about all y'all. And then I just kind of want to read up this little piece too. Even Carrier knew that his initial invention was not the most effective way to control humidity and continued tinkering with the technology. By 1922, Carrier had created the safer, smaller, and more powerful centrifugal refrigeration compressor, the precursor to modern air conditioning. At the Smithsonian National Museum of American History, one of the first practical centrifugal refrigeration compressors dating to 1922 is held in historic recognition of Carrier's feat. So there's so much more I could go into right now, but I'm just going to kind of touch on Gory and then Willis. And then I wanted to show you guys this as well. This is what the end result ended up being. Why is I have a notification. Okay. I want to show you guys this because it's super cute. This is what, can you guys see that? B, can you see that?
Okay.
Okay. This is what we ended up looking at in homes. And it is very much like giving off radiator vibes. And that's essentially all it is. A coil is a radiator. But it's just like so cute and small. And it makes me just really wonder how like we went from this to where we're at now as far as home air conditioning. But then also to look at this and know that this was the precursor to what Brett does. Like this is where we started, and now we're able to have rack refrigeration. Like that takes a lot of really smart people, really people with very big dreams and who are willing to take risks to make happen. So I just wanted to show you guys this kind of where it started before moving on to, what Brett's about to walk us through. So that's all I have, B. And you guys, if you have questions, we understand that this day got moved and it ended up really weird. So if you have questions that you want to ask, you can ask them in either Brett or I's groups. Brett's group is the Advanced Refrigeration Podcast Facebook group, and mine is the HVHX Coalition group. I'm going to stop sharing somehow. Here. Okay, there we go. And I'm going to give you back host.
Yeah, click me.
Take host.
All right, so now I can share. Oh, no, now you give it back to me.
There you go.
Share.
For those of you who don't know, Brett is in the, as I've said a couple of times, the supermarket refrigeration area of HVAC, and he just knows so much more about this than I will ever know. So I wanted him to come and talk to you guys a little bit.
Can you see my screen?
I can.
All right. Well, I just want to bring up Carl and Lindy because he's more
Yes.
of a badass than Carrier. So sorry. What is refrigeration? Basically refrigeration, just like air conditioning, is removing heat from, somewhere where we, don't want it and put it somewhere where we don't really care where it goes. Where there is no, there's no cold, there's just an absence of heat. So you always have to remember that people, have a hard time really kind of understanding that whole principle. And why do we have it, to essentially, to preserve perishable products and improve shelf life, and to, in order to maintain also creature comfort, which is us. Basic units of measurement. Cooling effect is measured in BTUs. It's weird after, the whole revolution thing, we didn't change it to something else, but now it's still British thermal units. That's what we've been using. 1 BTU is the amount of heat required to raise 1 pound of water 1 degree. We have 2 different types of heat. So, always remember this. We have latent heat and we have sensible heat. Sensible heat is something that you can measure, that you can actually feel the difference. So if you go from 35 degrees to 36 degrees, that's 1 degree of rise. That, you can feel that actual rise, and it's measurable with a thermometer. An instance of latent heat is when you have ice in a cup of water. That cup of water is going to be at 32 degrees. Even though you have both ice and water in there, it's going to still be 32 degrees. And even though the ice is melting and the water that it's surrounding is still taking away that, are adding heat to that ice, it's still going to be 32 degrees. Well, you can't measure that difference, right? It's still 32 degrees. There's still a change going on. That's the latent heat change. That's the change of state. So condensation, form of latent heat. Condensation, evaporation, both forms of latent heat, because we're changing state. 1 ton of refrigeration is equal to 12,000 BTUs.
And let's talk about where this came from too. So tons, you guys, we talk about tons in air conditioning, and everyone can't understand why we called it that, because, we have a ton, which is 2,000 pounds, and then we have tons in air conditioning. Well, the term ton came from ice. It was how much ice did it take to change the BTU output. So that is where the tonnage came from, was 2,000 pounds of ice, a ton of ice. And that's where that came from, just to put that out there.
Yeah. So the basic components of the refrigeration cycle, basically you have your compressor, and this is basically to increase the refrigerant pressure and pumps the refrigerant throughout the system. I mean, that's all it's really made for, is just to cycle that refrigerant throughout the system. The rest will be done throughout the process.
I don't know why I did that.
I don't know. Who let this guy in? Turn off. I'm echoing now, Dennis. You got to turn off whatever you're listening to me on.
Hi, Dennis.
You also have your condenser that is going to reject the heat. So in compressing, because we are, we're basically making them doing a mechanical movement in order to increase that pressure to get it to circulate around. A byproduct of that is going to be heat. And part of that process, through the condenser is also to reject the sensible heat, but then essentially then be able to change that vapor, that high pressure vapor into a liquid, so we can use it in the next process. Next, it's going to go along the pipe through the expansion valve, whatever that metering device may be. What does this do? This reduces the refrigerant pressure and controls the flow of refrigerant through the evaporator via superheat. And this can be a multitude of things, which I'll go through in a second. Um, that mix of liquid vapor then goes into the evaporator, which does exactly that. It takes that little bit of liquid that's still in there and uses that to absorb the heat of whatever we're throwing across that coil, essentially heating it up. But in that process, we also have that latent heat exchange again, where we're changing now all that liquid back into vapor, because this compressor is not a liquid pump. It is a vapor pump. And we all know that if we put liquid inside the compressor, it's not going to sound nice. They're not made to compress liquid. Now, this process not only can be done with mechanical operation, but this can also be done with, what's called absorption, what Jen was talking about before. I don't know if anyone here has ever stayed in an RV. A lot of RVs, they have a refrigerator, but it's a gas powered refrigerator. And how that works is they actually take, propane or natural gas. They heat up the bottom portion, which is heating up essentially an exchanger, and it's increasing the pressure of the refrigerant there. Essentially the same thing that we're doing with having a compressor. It's increasing that pressure and then driving it through naturally. They still use absorption systems now.
Yes.
There are some systems, they're called cogen plants. What they do is they generate electricity, and the byproduct is heat, right? You put whatever kind of gas, or, to make the combustion motor run in order to generate your electricity, but the byproduct is heat. So let's use that heat. So a lot of times what they'll do is they'll take that excess heat and then utilize that for something like a lithium bromine absorption chiller. They'll run that hot, usually transfer it over to water, instead of just having the hot exhaust, go travel all over the place. They'll heat that water and then use it for a couple different reasons. They'll use it to heat potable water. They'll use it to, heat, comfort cooling, or comfort heat,
Yeah.
right? And they'll also use it for the supply for those lithium bromide chillers.
Yeah.
So, and in this process, we have the high pressure, high temperature gas getting compressed, going through the condenser once again. We're rejecting that heat that we added in that compression process, then turning that high pressure vapor into a liquid, going through the expansion valve, dropping the pressure down, and then this is where the evaporator is absorbing that heat one more time.
Right.
Once again, think about refrigeration system as a transport system, much like power lines bringing electricity to us. Circulated moves the heat from one place to another, just like the power lines move the electricity from the generation plant over to us.
Right.
These copper piping systems are basically the conduit or power that's needed to drive the compressor and circulate the refrigerant through the metering device and throttle to increase and decrease the refrigerant flow based off need, just like electricity.
Yep.
Um,
Hey, Mac. Welcome, welcome. This is being recorded too. If anybody wants it for their students, it will be available in the SkillCat app.
so mind this, because Jennifer said that she was going to prep with me last night and then didn't call me until
In a
a half
mess.
an hour before. No, it's fine.
Red
So
covers for me no matter what. So I'm spoiled.
So the compressor, what is it doing? Once again, it's just circulating the refrigerant around. We have different types of compressors. We have hermetic compressors, which are hermetically sealed. There's no way to service them. So those would be the things on your self-contained units, small residential refrigerators, and smaller residential, ACs. We also have semi-hermetic ones that kind of look like, an engine, where you can actually service the valves and the pistons
Belt.
and everything else on that particular unit. We have screws. We have open drive motors, which are real nice because when you are adding electricity to an electric motor, right, you are generating some heat, and that heat sometimes is also transferred into that refrigerant. So, like, that's why we need a certain amount of cooling coming back to that compressor.
Yeah.
Compressors that are semi-hermetic, where I'm sorry, not semi-hermetic, that they're open drive, where the actual electrical is separate from the actual motor. Um, you're not adding any additional heat. It's just whatever is being circulated through that refrigerant system. So you're not adding any additional heat from the electricity that's being used to drive that motor. And then we also have CO2 compressors, which they're just
Yeah.
heavier constructed motors because we're dealing with really, really high pressures. Typical suction on a 20 degrees saturated system will typically run around 410 psi. The high side pressure, usually the high pressure switch is typically set for about 1540 on the high side.
Yeah.
Um,
This is what we see in our industrial applications, you guys.
yep, light, heavy commercial, supermarkets, and now they're doing a lot of industrial with that. Condensers, once again, the objectives of the condensers allow the refrigerant that has picked up the heat from that compressor and reject it to another location. The refrigerant changes state in the condenser and the operation from a high pressure gas to a high pressure liquid, changing the state, gives off that heat. Four main types of condensers. We have air cooled, water cooled, evaporative, and adiabatic. You might have not heard that term before. That's something that we just recently started using, probably within the past 10, 12, 15 years. Condensers usually involve rejecting heat outside or to a fluid. Sometimes you'll have a water cooled condenser on some chillers, on some refrigeration equipment. A lot cities are real big with that, especially like if you have a place, a high rise building. We actually have some supermarkets that are filled with self-contains. But if you had, I don't know, let's just say 60 or 120 different self-contains within that supermarket, you're going to generate a lot of heat. Well, it's going to make it really, really hot in there. So a lot of times what they'll do is they'll take a water-cooled condenser, basically a heat exchanger, take that heat once again where we don't want it and take it outside so we don't have to overheat that building. It's also sometimes uh, double used as comfort heating as well in the wintertime.
We call
So
that reheat.
yeah, essentially it's heat reclaim, right? We're reclaiming the heat that we would be generating and throwing out somewhere where we don't care, but then utilizing it for something that we need. These are some instance or some different styles of condensers. Usually they're made of copper tubing and aluminum fin. You can see this in stainless steel and a bunch of other material, depending on what they're doing. They're always doing a counterflow type process. So you see here, you have the discharge going into the top header, it'll go all the way out towards the end, and then the U-bends will bring it back and then go back and forth maybe one more time and then come out. And by the time we're about here, we've turned that refrigerant into a liquid. We always enter on the fan side where the fan is going to rotate, because if we were to put the hot refrigerant in here and run the fan all the way on the outside here, there's a high probability we could get some fluctuation. You'll have that heat exchange and you could actually warp that whole condenser. So notice usually when you have like even like a split system that's on a roof and you have two fans, if they do shut off one of the fans for ambient conditions, you'll see the one on the left-hand side closest to the header that's basically, turning on, or I'm sorry, the one closest towards the header, that'll stay on all the time. The other one opposing farther away from the header, that's the one that'll be cycling.
Yeah.
You have a evaporative condenser, which this is basically just dumping water across the tubing bundles, and using that as the media. This works really well in really dry conditions, because it's dependent on what the wet bulb temperature is. You get more efficiency out of it in drier areas. And you also have, yeah, this is what you're typically going to look like. So you have the tubing bundles that are in there. You're pouring that water basically over the condenser coils, and the fan is getting rid of that heat. The water drips down back to the bottom and gets recirculated, and off we go. Water cooled condensers, which I spoke of briefly. This is something, like I said, that we can use to exchange heat from one area to another. So if we want to keep our refrigerant charge down, we could have this water cooled water heat exchanger closer to the equipment, so that'll reduce our refrigerant charge, and essentially then just
Lobster
run the
place.
water across. What?
This is what we use at the lobster place.
The only problem is with water cooled anything. If anyone's ever had an old coffee pot, when after a couple months of using that coffee pot, you have sodium chloride, which is basically salt minerals that are left behind. Same principle with this. You're evaporating the water off. You're left with the hardness of that water, which a lot of times will lessen your efficiency of this thing, because now you have that little white particles all over the inside of the piping. So when you do have water cooled anything, typically there is some water treatment that has to be done.
Yep.
And then we have adiabatic. Adiabatic is something that we utilize a lot for CO2 systems. And, unlike the evaporative condenser, where typically we're dropping the water directly on the coils of copper going through, or steel, or whatever it might be made of. The difference here is we're not actually dropping it across the coils. All we're doing is, if you were to actually see a clear picture of this pad, it looks like, I'm sure Jennifer has seen a lot of these, the humidifier patterns, because as you're running heat, right, it's making it really dry. So you're trying to put humidity back into the facility, right? In this instance, we're just dropping water across this to drop the web bulb temperature of the air coming in, so we get more efficiency out of it. So if you had a regular, air cooled system, let's just say you have 10 degrees of TD, and what that means is your ambient added 10 degrees would equal your saturated condensing temperature, basically your pressure of what you're going to get on your high side. With something like an adiabatic, you're getting a 5-degree TD, which means that you can keep your head pressures lower. And if you can keep your head pressures lower, then your system's happier, right? You're not using nearly as much energy.
Absolutely.
Just give you that. So we also have the metering device, and that can be a capillary tube. That can be a thermostatic expansion valve. That can also be what we refer to as a bipolar stepper motor. Um,
Oh, I hate these so much. I have been fighting these all week long. I hate them so much. It's just so
why?
funny. They popped up in my face. I don't know. I prefer a TXV all day. I don't see them as much as you do though either. In your area, you guys use EUVs a lot more than we use them.
It's going to be everywhere.
Okay.
Even think about mini splits. They use them right at the condensing unit. That's why on the mini splits, the liquid line isn't really a liquid line. They actually
Right.
refer to it as a flash line, because there's an expansion valve there at the condensing unit,
Yep.
controlling that flow out to the evaporator. So
Absolutely.
you have the bipolar stepper, which it's a two pole motor that is driven electronically, usually with a DC voltage, anywhere from 12 to 18 volts, driving that motor open and close. And then you also have what are called uh, pulse width modulation, PWM. Those are expansion valves. They're ported solenoids. So
Those I
every
like a little better.
no, every solenoid is ported. That's what the size and the Sporlin numbers are. So if you see an S3 solenoid or an S5 solenoid, that's actually the port size. Well, they make ports that are smaller, more comparable to your tried and true mechanical expansion valves. You have the double A port, you have the triple A port, you have the A port, B port, and so on and so forth. Well, they have nozzles in here, that orifices that can be changed. So the valve, you can get the valve and you're like, oh, it's not big enough. But just like you can with the buildables, you can actually put a different orifice in there as well.
Love that.
Um, I feel like I'm beating this horse. Discharge line contains high temperature, high pressure, superheated vapor. Right. I want you to remember, any place that you have uh, gas, that it's superheated.
Yes.
Okay. So
Make the
here,
gas, we superheat it.
correct. So on this line, we have superheated gas going through the condenser, which is exactly what it sounds like. We condense it into a liquid. A lot of times on basic, even rack condensers, 99% of them, typically you'll get about 5 degrees of subcooling on there. Same thing with self-contains, same thing with single systems, split systems. You'll get about 5 degrees of subcooling. That refrigerant is then trapped in a receiver. We usually use receivers when we have a load that changes, so we can store that extra capacity of refrigerant. That refrigerant then has to be filtered. Once we filter it, just to make sure there's no particulates or anything from bad practices with Sporland's Panda to catch-all, going through the see-all filter, going through the liquid line solenoid, through Jennifer's expansion valve, and once again going back out through the compressor as a superheated suction gas. I talked about this briefly, and I just wanted to explain something because I mean a lot of questions that I get. Well, one of the biggest ones is, how do I know what the discharge pressure is supposed to be?
Yeah.
How do you know? Well, I mean, I'm very adamant at trying to figure out like what it's supposed to be, right? And this is the TD that I was talking about. So the TD is basically your air temperature in
Yep.
equal added to whatever the TD of the condenser design is, will give you a saturated condensing temperature, which would give you a pressure. I don't ever usually talk in pressure unless I'm just trying to explain, what equates to what. So in this example, we have a TD of 15 degrees. So we're shoving 75-degree air in the bottom of the condenser. And I'm not saying the air temperature is going to be 90 degrees. I'm saying that the saturated condensing temperature, basically the pressure converted, should equate to 90 degrees. Single systems, like self-contains and split systems, typically have a TD of about 20 degrees. So if you have a self-contained within like a gas station, gas station's typically held around 75 degrees. That means theoretically the saturated condensing temperature with proper charge, with the coil not iced up and everything like that, should equate to 95 degrees saturated condensing temperature. And all things have a different TD, right? So you have residential units that can be as high as 35 difference between the ambient, and you can also have as low as 25. And that's really what makes up your SEER rating, right? What is SEER rating? It's the efficiency of the unit, right? So what makes it more efficient? Well, how much energy usage it is, right? Well, the higher the pressure, right, the more energy it's going to use. Not really efficient. So if we're able to lower that pressure by having a bigger condenser to absorb more heat, or I'm sorry, reject more heat, essentially you'll save more energy because their head pressure is lower. So that's why I said some residential units could be 25, some residential units could be 35. It depends on how big of a SEER rating or efficiency that unit has. Supermarkets can range anywhere from 10 to 18 degrees of TD. And it really depends on what it was, what it was designed or what it was sized for. I'm using a lot of these terms, so this is a lot of good things to remember. Saturated, right? Saturated refers to when you have liquid and vapor in contact. So where do we have that going on?
That's when it's changing state, guys.
Yeah, so we have that right about here, right? Right where the nozzle is, right? Where else do we have saturated?
Macario, Steve, what do you see?
In the receiver, we have saturated, right? Because we do have.
Sorry, did I hear my name?
I did. I was just
What's
trying to
up?
make you guys up a little.
Oh, I'm here. I didn't know you were looking for active participation. I'm sorry.
We're just interacting right now. Do
Okay.
you see anywhere else on this that we have saturated refrigerant,
Let me actually
either
look.
liquid or vapor? Really?
Right there at the TXV on the, I'm guessing I'm gonna call that the left side.
Yep.
Entering into the evaporator, and you're gonna have it at the head pressure control valve. It looks like right there.
Yep.
Well, no,
And
No, it's not changing.
Well, here you just have vapor, right? So in here you have a mix of the two in the receiver, right?
Yep.
Essentially have liquid on the bottom, vapor at the top. So that would be a saturated mix, right? Right there would be a saturated mix. Anywhere else, it's either going to be superheated, or subcooled, right?
Yep.
All right. I'm still listening. I'm trying to cook and prep because
sure thing. Go for it. I was just trying to catch you guys off guard.
I'm going into downtown Dallas in a little bit for the Mavericks game. So I'm
Ooh,
here though. I'm listening.
No, I got you.
awesome.
Thanks.
So once again, superheated is anywhere that vapor is present, and only vapor is present, and subcooled is anywhere where liquid is present.
Right.
Subcooled is below or lower subcooled, lower measurement between the condenser and the inlet of the TXV. So you can have subcooled liquid anywhere from coming out from here through here into here. And that's basically the extent of it. And sometimes what we do is we have subcoolers in a lot of our industrial and commercial systems, which increase the efficiency of the system. I'm not really going to get into all that, but like, so we can, it's not just typically, 5 degrees. Like on your residential units, you can have what, 10, 12, as high as 15 degrees of subcooling on some systems, right?
Oh, higher than that even. We have usually typically between 14 and 20. So
Yep. Liquid line, 5 to 10 degrees, unless the system has a subcooler. On some single systems too, you have to watch on how the piping is, because sometimes you'll see a condenser where the refrigerant will go through, discharge, get that state change, and then come out, and then it'll go into a receiver, and then just before it goes back out down to the expansion valve, it might make one more pass and one available pass here, and
Yep.
then go back up, and essentially get just a little bit of free subcooling just from the ambient air.
Yep.
Evaporator superheat should be 6 to 8 degrees for medium temp, 3 to 5 for low temp, and for you residential cats out there, anywhere from what 8 to 12, sometimes 15 degrees of superheat, depending on how much efficiency they're trying to pull out of it.
Yep.
Compressor superheat should always be a minimum of 20 degrees. Why is that? Come on, Jen. Why should it be 20
asking me?
degrees? Yeah, I'm asking you.
Because it should always be a definite vapor.
Okay, so we're ensuring that what doesn't happen.
No liquid is flooding back to the compressor.
Correct. So it doesn't matter if it's Copeland, Bitzer, Manurup, whoever, they're going to tell you that we want a minimum of 20 degrees of superheat.
Yeah.
They also, in their literature, they also say no more than 65 degrees actual temperature. Now, think about a residential unit for a minute, okay? So we typically maintain a saturated of 38 to 40 degrees on our residential systems, right? Because we don't want to go all the way down to 32, because we go down to 32, we're going to freeze up, and the cat lady's going to be mad.
Yep.
So we want to make sure that we are getting the 20 degrees of superheat. So let's just say we're on a really hot day. We got 40 degrees saturated. So that would essentially give us our suction line temperature of 60 degrees, right? We added 20 onto our 40, and that's how we got a 60.
Yep.
If the unit is undercharged, that superheat would essentially be higher, and in essence, potentially make the suction line going back into that compressor higher than that 65. And start causing wear and tear on the compressor because of overheating, wearing down the windings, putting more.
And this also happens with a restriction, you guys, because when we have a liquid line restriction, we end up, starving the evaporator. Usually it's the same situation as if we didn't have enough refrigerant in the whole system, but really it's just trapped behind something. So you'll have those same symptoms, you guys.
Yep. Once again, superheated, and I know I'm, like I said, beating this dead horse, but she said it was refrigeration basics, so I didn't want to go all mad scientist on you.
That's the basics, baby.
Superheated vapor, once again, is heated or higher than the saturated. The measurement can be taken on the outlet of the compressor too, and a lot of people forget that. It's on the Copeland mobile app. They actually will show you.
I love that app.
If you actually put your saturated temperature in, as far as your saturated condensing temperature, saturated suction, what your physical suction line temperature is, and what your discharge potentially would be.
Yes.
The reason why that's nice is because if you have an instance where you have a compressor potentially shutting down for whatever reason, and you're like, well, I have these constants of what it's saying that it is, and it says that my discharge line should be 150 degrees. Why is it 200?
Right.
Well,
Why
there
for
may
the
be
split second am I getting different? Well, and bad windings will cause the same thing. If your windings are going weak, you'll have that same thing happen where it's only for a minute. It doesn't change it in total. It only changes it for a few minutes, and you're like, okay, something's going on here. I love that app so much.
Usually mechanical wear, right? Yep. You're gonna have mechanical wear that'll actually cause that.
Yep.
Let's see what else we got.
Can I say something about the saturation temperature that you were touching on just a second ago?
Please do.
I come from a residential world where everybody's real eager to hook up
They're gauges and gauge up.
Yeah.
Mm.
And what we are pushing over at Tech is that if you take your saturation temperatures, you take your line temperatures and use your rule of thumbs with your condensing 20 to 30 above ambient, you can get away from hooking up and kind of figure stuff out and being non-invasive. And I think that's very important.
Non-invasive system check. We preach it. We preach it.
No.
Kind of wish I got there sooner, right?
Yes.
Well, here's something else that you didn't, if you didn't know this. So if our system has distributor nozzles, now you're making me go back. Hold on here.
Brett's
Okay.
going down the rabbit hole.
Oh, he started it. So right on your distributor nozzles here, right? What temperature do you think theoretically that would be?
I have no idea. I don't even know what that is.
Come on, Miss MIT.
I don't work here. Okay, so it's gonna be where are we? Out at the
Right at the distributor,
evaporator?
past the pressure drop.
Okay, so it's gonna be high. Oh, past the pressure drop or before it?
Past the
Which
pressure drop.
direction we're going in?
Past
So
the
it's gonna be low then. We're gonna have low
low
temperature.
pressure, low temperature, low pressure. So what's it gonna be? It's gonna be
No.
hold on. It's gonna be, I'm gonna blow your mind. It's gonna be the exact saturated of what it would be if you would take a measurement. So that's the cheater way to see what your pressure is. Yes. No. So here, the reason why I can say that full-heartedly. Now, it might mess it up a little bit if you have a glided refrigerant. Okay. But years ago, before pressure transducers were very easy to put in and very prevalent, right? And I don't even know why I'm even explaining this to you, because you should know this. Because
why should I know this?
And I'll tell you in a second. So because they didn't have well, they did have pressure transducers, but the amount of money that it would take for all the cases to have pressure transducers would be quite expensive. So what they used to do is check superheat with sensors, the difference between the distributor tube there and the suction, because the difference on that would give you your superheat.
Right, but it will only do that if you don't have a blended refrigerant. That's why we don't do it anymore.
No, they still do it. They do it. The VRF that I installed, it doesn't have, it only has a main pressure transducer back at the condenser, but it has two sensors, one right on the distributor tube.
I don't know how that would work with 3 refrigerants and 1 refrigerant.
What do you mean?
Because you've got to blend, you've got to glide between your different refrigerants.
Okay, well, theoretically, it would be the midpoint.
Okay, so it's like an averaging. Gotcha. That actually would work.
Yes, it would. So that's my point.
That's another thing we can do in non-invasive system check, you guys.
So, yeah. So, I did a video.
Learning every day.
Not talking about that, but like talking about non-invasive. So remember how I was saying, like in your 75 degrees, 20-degree TD on top of that, which brings you up to 95. And then usually you get about 5 degrees of subcooling. So if your liquid line would theoretically be 90 degrees, then that's your non-invasive check. But once again, by checking, as long as you have a distributor now, as long as you have a distributor and
which we won't see a lot, you guys.
In residential, you see it all the time.
I don't know. Maybe on new residential units or on ones that are 410A, I'll say.
All right. But if you were to check right there where it's perfectly saturated, a mixture of liquid and vapor, like we just discussed.
Yeah, same spot for sure.
Theoretically, you should get the exact same pressure.
Absolutely.
All right, we already discussed that. You had me jumping back and forth. Okay. Don't do this. Gotta get rid of this thing.
Okay, I got it.
You gotta love it when somebody tells you, "Don't do this." I'm one of those guys that I'm immediately gonna do it.
No,
I'm still mind blown. I just want to go test Brett's theory.
All right. So anyway, so when you're mounting TXV bulbs, don't put it on
important.
Don't put there. Don't put it on a joint. Don't. Also, you're not supposed to mount these vertically.
Yep. Some are able to mount different ways. So make sure you know which way yours is supposed to mount before you mount it, guys. Causes serious problems.
The other thing is the
vertical thing. So could I reference my manufacturer's data for that?
Yes.
Yes. Yeah. So there's one. So
Brett probably has it memorized though.
See how it shows with the actual the pigtail up.
Yeah.
Right. You're not supposed to mount it with the pigtail down.
Right.
But follow your manufacturer, like, because if you look at like a Sporlan expansion valve in the book, because I'm lonely and bored, if you look in there,
Sponsored by Sporlan.
you'll be able to actually see that it'll tell you on which ways that you're supposed to mount that.
Yes,
Um,
it will.
uh,
But very
obviously-
important, the pigtail never goes down. Not in any application I've ever seen anyway.
Yeah,
Wow.
and you should have it at the equalization line. So a lot of your stuff is internally equalized, so it doesn't have the equalization line, but the bulb and equalization line should be about the same position.
Yeah.
So if your EQ line was over here, it should be mounted somewhere in here. The other thing is make sure that we're either anywhere from let's see, 3 to 2 o'clock,
Yeah.
and then it would be 9 to 10:30-ish, 10:30. The reason why is we don't want it on the bottom for a couple different reasons. One reason we don't want it on the bottom is because if you do have oil going through the system, if you put the bulb towards the bottom of the system, guess what? You're going to get maybe some of that insulation effect from the oil. So you're not going to get a true temperature of your refrigerant line.
Right.
You also don't want it directly on the bottom, because if you were to have, let's just say, lazy liquid feed, or you have an abundant amount of liquid feed, you could feed up with additional amounts of liquid, which is going to throw your superheat off. Yeah.
Dang.
Yeah.
Okay.
So what's the impact of facing that tail downward? Is that what you're saying?
Yeah, I'm not really sure. I
think from what I've heard about it, when I've researched about it, it won't work. So the vapor doesn't sit in the correct position, the liquid doesn't sit in the correct position, and then the metering device just won't read it correctly.
Yeah, so
a lot of those like that before.
Yeah.
Well,
Wow.
see, it's weird because if you're a residential guy, they're like, oh yeah, insulate the bulb all day long. Out of how many cases in a supermarket, they're never insulated.
Yeah, exactly.
Wow.
But it depends. Like, so on a walk-in where you have that outdoor on a walk-in where you're potentially like not, you could be affected by copious amounts of airstream. You know what I mean? Air, unit defrosting, whatever. Yeah, obviously we want it wrapped, but like in these cases, the coil is in the airstream, so like that's where they're like, it's not really getting a large effect of change. It's basically the same amount of change, but it's still theoretically you should have everything wrapped.
It's one of those deals where it will probably meter something. It just won't meter the correct amount.
It'll be fine.
Wow.
But don't do it.
Yeah, I know. I've just seen quite a
push
few.
the red button.
Wow.
All right, we kind of beat evaporators to death. Let me get down. Okay, so these are some different types of evaporators you might
Let's
see.
see some real ones.
This is you have
These are ones that Brett sees. These are not ones we see.
and we got some CO2. We got some CO2 ones here. We got some regular chemical refrigerant here. Sometimes you'll have evaporators that are in back walls, like typically right in front of here. So it looks like someone was cleaning this case. Right, not right there, but after. But essentially the wall had to be removed in order to gain access to the actual evaporator coil.
Right.
Those are some big industrial guys up there. You can see they actually have the door open and the distributor tubes hanging out there. And sometimes you'll see low profile units. I stated superheats before. I said 3 to 5 degrees for low temp and 6 to 8 degrees for medium temp. And 99.9% of the time that will be true. This is one of the exceptions to the rule. If you talk to the manufacturer for this type of case or this type of coil where you have two actual coils, they want 3 to 5 degrees of superheat because of the way that it distributes. Because otherwise, a lot of times on one side of this coil, you won't get superheat. You won't get a frosted coil. All your refrigerant will go to the other side. So on those low profile ones, 3 to 5. Once again, another example of how that airflow typically rolls. The air is sucked in, goes across the coil. We have to have the proper shelves in there. Otherwise, the air won't be distributed properly. Then you have an air curtain here, basically separating the warm ambient air to the cold air, and having that temperature difference really, kind of separates that. It makes a thermal barrier, if you will, right?
This is what happens when your restaurants leave their walk-in doors open too, guys, all the time.
Yeah. So there's a manufacturer of case that everyone dreaded. It was a 3 different chambered air coiled unit. So you had this primary coil, which was at -10. It was an open case. Then you had a secondary air that didn't go through the coil, but it was underneath this guy. And then
Yeah.
you had an ambient set of fans that would blow another third air curtain across it. So you could have
Wow.
one of those three fans messed up or thin wrong or something, and it was just humidity central. It was awesome.
Kidding. I was trying to find a picture on my computer of the evaporators at the lobster place. You guys, I'll share them in the groups because they're pretty cool. You guys would like those.
So once again, making sure we have the proper airflow. Now you do need to make sure that, like evaporators like this, the plenum is actually
Beat that horse, Brett. We were
Where the-
talking about this. Beat that
where the
horse.
plenum is all the way down. It's very easy to assume that, oh, it looks like it's down or the airflow is good.
Yeah.
No, and I'll get into
Sure.
why good isn't a form of measurement. And you're gonna be like, oh yeah.
Airflow is just as important in refrigeration as it is in residential HVAC, you guys. It's always ABC, no matter what you're doing.
Yep.
I was just talking about this before this.
All right. So rooftop unit, outdoor units, outdoor machine rooms. This is an outdoor facility. Sometimes you'll have, the mechanical rooms that are actually inside the facility. It depends on how how the system was designed, right? This is just a pictorial with some things to look for. Like this is an evaporator pressure regulator. There's your suction port there. There's where your TXV bulb should be. There's your TXV, and there's your adjustment stem on your EPR. And the EPR is an evaporator pressure regulator. Essentially, if you really think about it, we only have three different types of valves that we deal with. I know there's hundreds of models and model numbers all over the place, but really there's only three different types of valves. And you're going to be like, no, you're full of it. And I was like, no, no. Listen, there's only three different kinds of regulating valves. You have an inlet pressure regulator, outlet pressure regulator, and differential. That's it.
Yeah, I guess you're right. If you go that way with it, yes.
100%. It doesn't matter the model number. It's still doing one of those three things. In this instance, the EPR is on the outlet of the evaporator, right? So that is an inlet pressure regulator.
Right.
I want to get down to the diagnosing stuff. Oh, man. All right. Well, here I already jumped ahead.
Yeah.
All right. So inlet pressure regulator, some instances we have, evaporator pressure regulators, holdback valves. You've probably seen a bunch of these different things. Commercial refrigeration, you'll see something like that. Commercial, you'll see something like that. Same thing with that.
Yep.
Sorry to interrupt. Holdback valves, is that the same as a holdout relay?
No, holdback valve. That would be like a condenser flooding valve.
Right.
Okay, gotcha.
Like to control head pressure on low ambient, right?
Yeah.
Mm-hmm. Okay.
Yep.
Thank you.
Hey, Dizzle.
So then we have outlet pressure regulator. So some different types of valves. You have hot gas bypass, receiver repressurization valves, A8 AOE, which is a liquid pressure regulator, and also the CROT, which is a crankcase pressure regulator. So that's usually used on low temperature refrigeration systems that, if you have a low temp system that only has one compressor and you put that system into a defrost, that you're going to have a very heavy heat load that you have to now pull down. So if the temperature is too high, that means your pressure is going to be too high. And there are, if the compressor is only sized for X, for the actual running load and not the full defrost load, we got to make sure we kind of mitigate that pressure down to the evaporator. And that's essentially what a crankcase pressure regulator does. Let's see what else we got. Jumping ahead here. Oh. Sorry.
I don't know what that is.
Well, some examples of expansion valves that are really, 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 really dirty.
Yep.
So let me get down to this. Sorry, I was jumping. Oh, the last regulator before I forget is a differential regulator. You guys have also see those, the head pressure controls. You'll see a differential, which looks like a little bullet. Usually on Sporlan, it's ORD, open on rise of differential. All those letters actually mean something. That's what happens when you're bored.
Not just an ORD valve.
Yeah. Like OLDR, open on line differential, or open on liquid differential regulator. Like I said, all these letters actually mean something. But let me get down to the diagnostic stuff. All right, so here's the ABCs of HVACR. Now I'm going to talk about Sesame Street stuff. I'm talking about ABCs, meaning what you should be doing when you diagnose any piece of equipment. And it doesn't matter if we're talking about a rooftop unit, it doesn't matter if we're talking about an air conditioner or even a refrigeration system. It's still, all this theory still flies.
Yes.
So airflow is first. ABC stands for air before charge. So I have to make sure that airflow is right. So if you're dealing with a rooftop unit, like obviously you're not going to go down to every single duct to make sure, okay, I have this CFM. But what you can do is measure your amperage of your motor and make sure that that's running the full FLA. And a lot of times you'll see on a on a rooftop unit, you'll see the belt sucked in all the way to the middle of the pulley. That's actually the drive pulley, right? Well, before I explain anything else, imagine, if you will, a mountain bike. I'm sure everyone here has ridden a mountain bike. When you're on the little gear on the front, you're pedaling really, really fast, but not a lot of energy is being done to the rear tire, right? Well, if you put it on the bigger gear in the front, now it's a lot hotter. You're putting more energy in there, and now it's actually doing more work. So if that essentially chain is on the little part of the pulley, it's not doing any work to the blower and not moving the proper amount of airflow. So a lot of the ones have the variable pitch pulleys where you can thin them up a little bit and get that thing riding right on the edge.
Yeah,
So
make sure you're adjusting pulleys on maintenance, you guys. If you're not already, check them. At least check them. If they're good, they're good. If they're not, you can adjust those.
That is an outstanding visual. Kudos.
Isn't that perfect? He's so good.
Yeah, that's good. That is outstanding, fella.
So, anyway, so back to this. So when we look at we look at the airflow first because it can affect our saturated suction as well as our superheat, and I'll get to why those are important in a second. So in supermarket refrigeration, commercial refrigeration, if you look up any IOM, there's installation, operation, and maintenance book. Once again, boring. So you can look up what application it is, if it has doors, if it doesn't have doors. It'll give you the BTUs based if it's a conventional system or a parallel system, and all that really means is single system, single condenser, parallel meaning rack. Okay. Then you have your superheat set point of what it should be. You have your evaporator temp, which is your saturated. Once again, it doesn't know what refrigerant it's running. It just knows what saturated suction it was designed for. That's why I'm like, I don't want to talk about pressures. I just care about saturated. And then it tells you what discharge air you should get if you have proper airflow, proper saturated, and proper superheat, which means you'll get about -6 degrees coming out of the honeycombs for your discharge air. So this means that this unit has a 6-degree TD. If we're maintaining a -12 here, we'll get a -6 on the outlet here. Okay, so this has a 6-degree TD. So the reason why all this stuff is so important is because you can't just walk up to a piece of equipment, and if you're on the phone with me, and you can't just say it's good.
Right.
Good isn't a form of measurement, man. Because I had a cat that called
and say that.
Yeah. I had a guy that called me up and he said, yeah, the airflow is good. I checked it with my hand. I wet my hand. It's good.
It's flowing.
And so I'm like, dude, I don't know what's wrong, because he was telling me all the rest of the stuff. It doesn't make any sense. So he went back the next day. This is a case that was running fine. It was running at 163 feet per minute. Okay. So remember, we're only doing feet per minute, not cubic feet per minute, not rooftop stuff.
This is a CFM, you guys.
Okay. He measured the case that wasn't working. He had 360 feet per minute. And sometimes diagnosis is using your powers of deduction. Now I'm going to blow this picture up just so you can see it a little bit better. So just by looking at this, okay, I can tell you a couple things about this. I can tell you this is a different fan, and I don't even see the other fan right now. If this is the only picture I was sent, one of the things I'm seeing is that, look, the screw holes aren't exactly all center. So I can tell you right off the bat, someone put this in after. The second thing I could tell you for sure that someone put it in a second one, because you could see a little dirt ring around the edge, which means the old fan was a little bit bigger. You can see an old existing screw hole here as well. So someone put the wrong fan in there, and that's essentially what this problem was on this particular case.
Yeah, you guys, we always talk about it when we do our troubleshooting classes, that the best tool you have is your own eyes. Like, look around, check out every single piece before you ever put any gauges on a system. Make sure you're using your visual troubleshooting and diagnostic before you do that.
So his problem on this particular system was he had a 5-pound pressure or 5-degree saturated increase than what he should have. Like, he actually measured on this case over here, in this case over here, and they were getting a lower saturated versus this one. So just this case was getting a 5 degrees higher, which was like I think 3 psi or something like that, or 4 psi.
Yeah.
And it was because the fan was moving so much air across, it was causing the expansion valve to open up as wide as it could just to funnel as much refrigerant through as possible.
Yep.
And then in essence, just, load that little 5/8 lineup with too much refrigerant, which made too high of a pressure drop because it wasn't made for that quantity of refrigerant. This coil is only 2,900 BTUs. It was probably shoveling 3 times that amount through that same, little suction pipe.
And that's why it froze where it did, you guys, too. On those pictures, you can clearly see what's frozen and what's not, and that's why it did that.
So this is Brett's triangle. I'm calling it Brett's triangle because I haven't seen this before ever, and I'm just going to take credit for it because I don't take credit for it.
I'm stealing it.
No, you're not. So once you found the information in the IOM manual and you found the online for your case for your investigation, when you start to check the operation, remember you need 3 different things. You need airflow, you need superheat, and your correct saturated suction. So what you would do is we said we're going to check our airflow first, right? So if Mr. Good would have told me that this is what he got on the first one, we would have said, okay, stop there, get it fixed.
Yeah.
Because anything else that he's going to do is just going to try to band-aid anything. So when he went back to here, he changed this out because he wasn't maintaining a -12 saturated suction. He was maintaining a 6 degree or minus 6 degree saturated suction, which means he was only getting -6. He was only getting a 0 degree box when in essence he should have been getting a -6 because his saturated was high. That's why I said airflow can affect the superheat as well as the SST. So check the airflow first. Once you have the airflow, so once you replace the fan, everything else would have went into place. If it didn't, you would have checked your SST. Your SST typically has to be at the design or maybe 2 degrees lower than that.
Yeah.
Any lower than that, you actually affect the whole coil size, which I'm not going to get into because that's a whole nother can of worms, and I don't have another hour.
Yeah.
So then, so once we check this and we check this, the only other thing that could be messed up would be our superheat. If we have our airflow, we have the correct SST, and we have the correct superheat, triangle solid, that case should pull down. If you don't have one of these 3 things, triangle collapses and you're underneath a refrigerator crying by yourself.
I just love this picture so much. It's just very me.
So
all right, you guys, if anybody has any questions for Brett, now's the time. You can also, I said it in the beginning, but you can also post in either of our groups. If you guys aren't members of the Advanced Refrigeration podcast group, go join it on Facebook. And also the same goes for the HVHX Coalition group. Make sure you're joining up so we can continue these conversations.
Brett, I don't really have a question, I have a statement. And this also goes for Jennifer. I appreciate you taking your time out to do stuff like this and sharing your information and the stuff that you had to learn through trial and error.
Anytime.
It's very valuable and it's much appreciated. I just have a hell of a hard time finding the time to join them.
You're doing a really good job today. All right,
I'm swamped, man. Woo.
Yeah, we're all slammed, but this is a future. This is what we got to do.
There's 24 usable hours in every day, sir.
Yeah, I'm trying to learn how to be a teacher, and I had a very
and I'm not going to Mavs game.
Yeah.
Actually, yeah. So Mac, you and B are very close together right now, and so Mac teaches at what school is it, Mac?
Lincoln Tech in Grand Prairie, Texas.
I listen. I've talked to Mac. He was supposed to look at some slides and then blew me off.
Oh yeah.
Oh, man. You know what I did? I fell asleep.
I do it to him all the time. Last night I was supposed to prep because I begged him to come and do this with me, and then I fell asleep, blew him off this morning because I had to go get parts, and he still showed up because he's the best.
I will tell you, I underestimated the bite that I was biting off with the teaching thing.
Yeah.
But I have a documented history of running towards challenges. So
that's good.
It's been great. It's been great. It's been awesome. So I love it. But
students don't care as long as you're not teaching them wrong.
Oh yeah, we have those conversations daily inside our house over there. Yeah. We sure do. But I do appreciate it though, Brett, very much. And also Jennifer.
I do too. Thanks, B. Thanks for coming on with me.
Absolutely. Anybody?
All right, you guys, we're gonna. Oh, nope. Go ahead, B.
I was just gonna say, anyone have any more questions?
Going once, going twice. And again, you can put them in the groups if you guys want to ask them, virtually, no problem at all. Brett is always there to answer questions. And that's why he's my bestie. And thank you, Brett, because I learned 2 new things on this deal. So I'm really excited about that. So
Cool.
Thanks for teaching me too.
I've taken some screenshots. I'm not stealing those, but I'm totally stealing your bicycle chain analogy.
It's so
like,
good.
I was in,
rolling, buddy.
dude. I was in a class the other day. Oh, no, actually, you know what? One of the mentees that Jennifer gave me lives down in San Antonio, and I was talking to her, and that's the that's the third time I've only used that analogy. Like I was trying to figure out a way to explain it. And that's one cool thing about teaching. A lot of times you can take something and you've tried to explain it 50 different times and like cats don't understand it, but it just takes that one, make that light bulb go off and you're like, shit, that works all the time. So like explain it that way.
That's a good one though. I remember when you were saying that, I was thinking about the way that my professors explained, thermal work to me, and that would have actually been perfect. Like any type of work is perfectly described that way. So yeah, if you're a teacher, go with something like that, because that's something that I will never forget now the rest of my life. It's the way that he explained that.
Yeah, neither will I. Neither will I. Absolutely.
All right, you guys, thank you so much for coming. This recording will be available in the SkillCat app probably tomorrow, I would assume. Usually it's about 24 hours, and I know we're not on our regular day, so I really appreciate everybody who came. And if you want to share it, you'll be able to. I will put it in the HVA Chicks Coalition group after it is uploaded to SkillCat app tomorrow. And if you're not a SkillCat member, go and join SkillCat and use HVA Chicks for a discount code. And
thank you. Y'all be careful.
Thank you, guys.